Hey guys, this is the last new thing we are going to learn from chapter 5. All right, then we have 3 review days, so your test is next Wednesday, all right? Determine if 2 events are independent. That's the first thing we're going to do. And then, when appropriate, use the multiplication rule for independent events to compute probabilities. So you guys, we learned yesterday that you can check independence with this formula, which is not on the AP exam, and you need to memorize that, okay? The probability of A given B equals probability of A. Whatever you put first is what you need to put on the right-hand side, okay? So you may need to use that formula for independence, and sometimes you can just think through if you have independence, all right? So what happens to the general multiplication rule if we have independent events? So you guys, we learned with our tree diagrams, you are always allowed, this means and, okay, which tells you to multiply, okay? You are always allowed to multiply the probability of A times the probability of B given A, all right? This is the conditional. Basically, I know something happened, so then what's the probability of B? Okay, those are your tree diagrams, those types of things you're always allowed to multiply. However, I can also just multiply A times B, probability of A times probability of B, if the events are independent. Okay, anybody notice something right here? This equals this. That's the formula for independence. It's just in the other order. Okay, that says right there the probability of B given A equals the probability of B. If those are equal, they are independent. Okay, so when do we have independent events? For example, if I said, what's the probability of flipping a heads and then getting another heads on a coin and then getting another heads, what would you guys do? 1/2 times 1/2 times 1/2. Does that probability change each time? No. Okay. Does what happened on the first flip matter for the next flip? No. So they are independent events. All right. Same if I replace the cards in the deck, right? So in other words, I'm constantly drawing cards and my probability would be out of 52. Those would be independent if I replace the cards. So if you're sampling with replacement, you know you have independent events. All right. So just to review here, what does this symbol mean right here, you guys? Or, okay? And or means add. Now, you can only do the simple adding formula, like add A plus B, if the events are, what's the vocab word? Yes. Okay, you can only just add A and B if they're mutually exclusive. If they're not mutually exclusive, you have to subtract what you double counted, the overlap. Okay? So same thing here. I can just straight up multiply because this guy means and, which means multiply if the events are independent. All right, so you're checking for mutually exclusive to just add. You're checking for independence to just multiply the events. Okay. The Challenger disaster. On January 28th, 1986, Space Shuttle Challenger exploded on takeoff. All 7 crew members were killed. Following the disaster, scientists and statisticians helped analyze what went wrong. They determined that the failure of O-ring joints in the shuttle's booster rockets was to blame. Under the cold conditions that day, experts estimated that the probability that an individual O-ring joint would function properly was about 97.7%. But there were 6 of these O-ring joints, and all 6 had to function properly for the shuttle to launch safely. Assuming that O-ring joints succeed or fail independently, find the probability that the shuttle would launch safely under similar conditions. So right here, you're like, oh good, I have independence. I'm allowed to multiply. So a lot of the times, they're just going to tell you the events are independent. And you're like, thank you, problem, for telling me that. Now I know I'm allowed to multiply. All right. So what's the probability the shuttle would launch safely? Well, in order for the shuttle to launch safely, we need all 6 O-ring joints to succeed, right? So I need the first one to succeed, and the second one to succeed, and the third one to succeed, and the fourth one to succeed, and the fifth one to succeed, and the, oh, I didn't, oh, 6. I was on a roll there. I wrote 6. Okay, and the 6th one to succeed. Okay. So what's the probability the first one succeeds? 0.977. And what's the probability that the next one succeeds? 0.977. And 0.977. And 0.977. There's 4. There's 5. And there's 6. They are independent of each other. So it doesn't matter what the other one did. You're allowed to just multiply them together. All right. And when you multiply all of these, we get 87% chance, okay, that all 6 of them succeeded. So I don't know if you guys would take your chances on a rocket if you knew it was an 87% chance of success. But they were the unlucky 13%. Okay? So what is the probability the shuttle would not launch safely? There you go. It would be 13%. All right? Which would actually be this right here. And you should write this formula down. It is super important. Okay? Whenever the problem states at least 1, you need to use this formula, 1 minus the probability of none. So in the previous problem, when it asks for the probability that it failed, so you guys, we only needed one of those to fail, okay, for the whole thing to explode, all right? Just 1 out of the 6. So the probability of at least one of them failing is what we're looking for. At least 1 fails is 1 minus the probability that none fail, okay? And I'm showing you this because a lot of times they don't give you the part A that we just did, okay? So if they give you the part A, yes, you can be like, oh, it's 13% because I just did 87%, so I know this, all right? But they may not give you that. You might have to start with this, okay? So 1 fails. I'm going to do 1 minus probability that none of them fail. So what's the probability none of them fail, meaning that they all succeed, okay? Which would be to the 6th. They all succeed, right? And that would be 1 minus, of course, that 87%, which is the 13%, okay? All right, so here's one where they're not giving you the part A. You have to be able to do at least 1. All right, so rapid HIV testing. Many people who visit clinics to be tested for HIV don't come back to learn their test results. Seems strange, all right? Clinics now use rapid HIV tests that give a result while the client waits. The trade-off for fast results is that rapid tests are less accurate than slower laboratory tests. So applied to people who have no HIV antibodies, okay, they do not have HIV, one rapid test has a probability of 0.004 of producing a false positive. So they are going to tell them that they have HIV when they don't. All right, that's the chances. All right, what if we pick 200 people randomly who are free of HIV? They don't have it. What's the probability at least 1 false positive will occur? Okay, assume that test results for different individuals are independent. And you're like, oh, thank you, problem, for just telling me this, so I know I'm allowed to multiply. All right, they do that a lot. So probability of at least 1 is 1 minus probability of none. But you have to fill in some words here. Like, what is it actually saying? At least 1 what? There you go. We're looking for at least 1 false positive test result. All right? That would be 1 minus probability of none. But what does none mean? No false positives. All right? Okay. So I'm going to do 1 minus. Okay, I want no false positives in all 200 people. This is the probability of getting a false positive. What's the probability of not getting a false positive? 0.996. You guys, this happens a lot in these problems where they're giving you what's called the complement 1 minus, okay? So the 0.004 is the probability of getting one. This is the probability of not getting a false positive. And how many times do we need that to happen? 200 times. All 200 people, all right? We end up getting 55% for this problem, all right? So it's a 55% chance that out of 200 people who don't have it, at least one of them will get a false positive test result, even though none of them have it. Okay? All right, beware of lack of independence. When they don't tell you something is independent, or they're asking you, can we multiply these? You're going to need to think through if you have independent events, okay? So Littleton and Highlands Ranch are two neighboring suburbs in the Denver area. According to a local newspaper, there's a 50% chance of rain tomorrow in Littleton and a 50% chance of rain in Highlands Ranch tomorrow. Does this mean that there's a 0.5 times 0.5 or 25% probability that it will rain in both cities? No, that makes no sense. If it's a 50% chance of raining here in Littleton and it's a 50% chance of raining in Highlands Ranch, it's probably pretty likely like 50% chance that it'll rain in both cities, or maybe like 48 or something, right? But it probably doesn't drop that much because are these events independent? No. If it rains in Littleton, does that increase the chances of rain in Highlands Ranch? Yes. All right. They are closely located cities. Now, if I was doing the weather in New York and the weather in some city in California, probably independent. All right. Sometimes it's up to you to explain it. So if you're not sure, you should probably say on the AP exam, I'm going to assume these are independent and that like the weather here does not affect the weather here. Or you could say, I don't think these are independent, and because like what happens here does affect what happens over here. All right. So you guys, this would just be like, no, I cannot do this problem. And you would write this down and you'd be like, nope, okay, that's it. All right. Is there a connection between mutually exclusive and independent? Okay. If someone is male, biologically, all right, they're over here in this circle. And if someone is pregnant, they cannot also be male, okay? So these two circles are what? Mutually exclusive. Now, if I know someone is biologically male, what do I know about them being pregnant? I know they're not pregnant. So are these independent or dependent? Yes. If I know this, don't I 100% know they're not this? And if I know this, don't I 100% know they are not that? Okay, so those are not independent. So something I would most definitely write in my notes. If two events are mutually exclusive, then knowing one event occurred definitely affects the outcome of the second. So they are not independent. Mutually exclusive events are not independent, because once you know one thing, you know the other thing does not happen. And similarly, independent events must have overlap. So if you know you have independent events, then they must not be mutually exclusive. Okay, independent events have overlap between the two circles. Yes. I have to think about what the two things would be, like what your two circles would be. Yeah, and those would be separate. I'll have to think about it. I'm gonna think about it. All right, you guys. During World War II, the British found, hold on, that the probability that a bomber is lost through enemy action on a mission over occupied Europe was about 5%. Assuming that missions are independent, find the probability that a bomber returned safely from 20 missions. All right, we've got some dark examples today, all right? Challenger example and World War II, all right? So you guys, we want to return safely from 20 missions. You could write safe and safe and safe and safe 20 times, or you could just say probability return safe 20 missions. Okay? Equals. Okay, what's this 5% again? Okay, the probability they do not return safe. So what's the probability they return safe, you guys? Yes, 95%. Okay, that's the probability they return safe from one mission. Okay, and then we would want to be the next one, and the next one, and the next one 20 times. So it would be 0.95 to the 20th, which is actually only a 36% chance. So don't fly during World War II 20 times when your chances of not returning are 5% each time, okay? And one more example. Government data showed that 8% of adults are full-time college students and that 30% of adults are age 55 or older. Because 8% times 30% is 0.024, can we conclude that about 2.4% of adults are college students 55 or older? Why or why not? Essentially, they're asking, can I multiply these together? Which basically means, do I have independent events? So up here, you guys, I forgot to point this out. They told us we had independent events. All right, if they're asking you, it's probably no, all right, because they're probably trying to get you to think through it. But why are they not independent is the question. So no, you guys, you can't multiply these together because they're not independent. But why is that? Yes, and think about what you guys does. Like if I'm like, oh, I have a group of college age or college people, people that go to college. What age are they usually? Yeah, it tells us something, right, about like what age they are. I would be like, yes, it is way more likely if you're going to college that you're like 20 years old than 55 years old. All right. So that means they're not independent. If it was proportional, they would be independent, right? So in other words, if we had the same number of 20-year-olds as 30-year-olds, as 40-year-olds, as 50-year-olds going to college, they would be independent. But those are definitely not proportional. If I know somebody is in college, it's a high likelihood they're young. Does that make sense? So these are not independent events. Therefore, we cannot multiply. All right, you guys, grab this worksheet. Let's try it out.